everyone. Today we will study the Wagner Meerwein rearrangement. It is one of the most important rearrangement which is asked in the competitive examination, also in the university examination. It is named after its discoverer Igor Igorovich Wagner. The migration of alkyl group to a cationic center is known as Wagner Meerwein rearrangement. This rearrangement or shift have been studied extensively in the class of natural products such as acid catalyzation of camphenol to stannine, isobornyl to camphene, and many more. Let's see some of it. Wagner Meerwein rearrangement is a 1-2 shift rearrangement in which hydrogen or the alkyl group present near a cationic center migrates from one carbon to a neighboring carbocation, From this we understand here a carbocation is formed and the Gris group such as alkyl, aryl or hydrogen is migrated. Let's see some of its application of Wagner Meerwein rearrangement. First is the acid catalyzed dehydration of natural product, that is camphenol to stannine. Stannine here is a key component of the fragrance of the sandalwood oil. In this camphenol to stannine, the migration of this methyl group takes place as due to this H, in presence of this H plus ion is abstracted by this OH and water molecule is formed, and the water molecule is a good living group and it is departed, and this migration of methyl groups takes place. Let's see its detailed mechanism. You may have questioned why only this methyl group is migrated. Over here also there is an hydrogen, so it can also be migrated. So here is the two possibility. Let's see first the migration of the hydrogen. So as we have seen earlier, the it takes place in the presence of H plus ion or any Lewis acid. So the hydroxyl group takes the proton and formed a water molecule, and this water molecule depart, and a secondary carbocation is here. The secondary carbocation is formed. If this H is migrated, then in the bridgehead position formation of the alkyl group will be formed. And we know that alkene cannot be formed at the bridgehead position because it will create a very bridgehead strain and which is not stable. So this reaction will not be taking place. Now we will see the migration of the methyl group, which is the second possibility. So this is a secondary carbocation and this methyl group is migrated, and over here after migration a tertiary carbocation is formed, and this tertiary carbocation is neutralized by the elimination of this hydrogen atom, and here the alkene is formed. From secondary carbocation it's formed a tertiary cation which is more stable, because we have studied in the stability of carbocation that tertiary carbocation is more stable than secondary, and secondary is more stable than primary. So the migration of methyl group both stabilizes the cation as it becomes tertiary instead of secondary, and also allows the elimination to give a stable alkene. So we will see the next example, that is acid catalyzation of dehydration of isobonyl to give camphene. By seeing this rearrangement, it's look quite complicated, but it's not so complicated. In fact, only one alkyl migration is involved. One important point you should remember in the rearrangement is that number of carbon atom will never change. Only their rearrangement takes place. So for the simplicity, we will give numbering as you can see here, we have given the numbering to all the carbons present in this molecule. And this product also. What is the difference you can see? Over here, the fourth carbon and the fifth carbon bond is broken, and the new bond is formed between fourth and the sixth carbon. Means this fourth and the sixth carbon forms a bond. So as we have seen in the earlier example, this OH will abstract the proton and OH2 plus will be formed, and which is the water molecule and a good living group, and it will depart. And the formation of a carbocation at the sixth position will take place. And it is also a secondary carbon. This carbocation is next to a tertiary quaternary center, and the migration of all the three bonds cannot take place because it cannot generate the most stable carbocation. But we have seen the new bond is formed between fourth and sixth, so this fourth bond will be migrated. And the bond between fourth and sixth carbon is formed, and a carbocation which is more stable is formed at the fifth carbon. When we will do some rotation in this structure about 180 degree, we will get this kind of structure. Over here, this hydrogen departs and formation of an alkene group takes place, and we will get the product, that is a camphene. And it is a very stable compound. The next application is ring expansion. More stable usually means more substituted, but cation can also be made more stable if they become less strained. So for example, this 4-membered ring rearranged to give this 5-membered ring in order to relieve strain. Here the cation formed due to protonation of an alkene group. Let's see its mechanism in detail. Here the carbocation is formed due to the protonation of alkene, and here it is a carbocation. This carbon 1 migrates to carbon 5th, and a tertiary carbocation migrates to tertiary carbocation, and here the secondary carbocation is formed. You may have noticed here the stable tertiary cation transform into the less stable secondary cation, but here the strain is relieved. So more preference is given to the ring expansion and relieve the strain than to the stability of the carbon. Let's see its example. But before going on to it, this chlorine attacks this carbocation and a chloride addition to the cation takes place. So let's see the example, that is a synthesis of alpha carophyllene. Firstly here 2 plus 2 cycloaddition takes place photochemically. This leads to the formation of a 4-membered ring. Then in presence of methyl lithium, this methyl group attacks to the carbonyl carbide and hydroxyl group is formed. First we will number the carbon, and here you can see the carbon 7 migrate to carbon 5 from carbon 6. Let's see its mechanism. Due to the acid catalyzation, the loss of water molecules takes place, and here the tertiary carbocation is formed. This carbon 7 attacks on the carbon 5th to form a 5-membered ring and a secondary carbocation. This secondary carbocation is attacked by a water molecule and a hydroxyl group is formed. So this is all about the today's topic, that is Wagner Meerwein rearrangement. I hope whatever we have gone through is very clear to you. If not, you can ask your doubt in the comment section. Please do not forget to like and share this video. Subscribe for more organic chemistry. So thank you.